Hello and welcome back. In section 2.3, we get to work with continuity. So first we'll sort of look at just some rough unscaled sketches, working on an intuitive idea of continuity, and then we'll get to a more formal definition using limits. So one basic function that you're all familiar with that is not continuous, at least in one spot, the reciprocal function. This one is actually the opposite of the reciprocal function. So basically f of x is opposite of x. We have a continuous curve, continuous curve, continuous curve, and then a jump, and then another chunk that is hooked together. But in this one spot in the middle at x equals 0, we have a discontinuity. We have a jump, a place where one part of our curve doesn't touch the rest of the curve. The greatest integer function, if you've ever seen that one, looks like a step function. I'll just draw the q1 part and x-axis part. Again, not a continuous function. We've got these gaps in here. Even some rational functions where there's only a hole. That's one spot where we have a discontinuity, and that would be whether or not we also had some other point not equal to where the hole was. So with or without the red dot, that is still not a continuous function at that point. So the basic idea of continuity is that you can sort of draw the graph without picking up your pencil. So it can have as many curves as you want, go as high up or low down as you want. You just can't pick up the pen or pencil you're working with and still draw the graph like I had to here or here or here. Now, as far as what that looks like with a more formal definition, f is continuous at x equals c if we meet three conditions. F of c exists. Limit as x approaches c of function f of x also exists. And the key last one, f of c is the same as the limit as x approaches c of function f of x. So those are the three conditions. So for example, in our first one at x equals 0, we broke the very first rule. It doesn't exist there. The second one, this exists for all values of x. We would be able to keep going this way as well. But the limit at, for example, x equals, say, 1 here, left side and right side don't agree, so that limit does not exist. Or in this third case, the limit exists and it has one value. The function has an output at that, but it's a different value, so they don't match. So this one breaks the third rule. So we have to have an ordered pair at that x value. The limit has to exist, and those two values do have to agree. That is what would prove continuity at a certain point. So for example, we'll look at f of x is x squared plus 2x plus 1, and we'll show f is continuous at x equals 3. So let's see if we can find all three pieces. So we'll see if f of 3 exists. F of 3 squared plus 2 by 3 plus 1. So 9 and 6, 15, 1 is 16. So f of 3 is 16. So part 1, done deal. This ordered pair does exist. We do have an output for an input of 3. So we can move on. So then we'll take a look at the limit as x approaches 3 of the quantity x squared plus 2x plus 1. So notice multiple terms, so that got thrown in parentheses. This would also be worth 16. We can simply plug in the 3 here and it does work. And since those two values agree, we do have continuity at 3. The 3 dots there is mathematical shorthand for the word therefore. So therefore f is continuous at x equals 3. All right, so let me have you all try one out. So g of x is going to be x squared minus 16 over x minus 4. And see if you can determine if this is continuous or not continuous at x equals, we'll try 0 and 4. Okay, so see if you can run through this sort of 3-step process for each of these 2 points. Go ahead and pause it, and we'll return once you hit play. Okay, welcome back. So first the 0. So g of 0, 0 squared minus 16 over 0 minus 4, which is negative 16 over negative 4, which is 4. So g of 0 is 4. If that doesn't exist, we're basically done. Since this does exist, I do have a real number for an output. I can move on and check the limit. So I'll check the limit as x approaches 0 of x squared minus 16 over x minus 4. And on that one, we can in fact just use the substitution. So we have negative 16 over negative 4 again, which is positive 4. So g of 0 is the same as the limit as x approaches 0 of function g of x. Therefore, g is continuous at x equals 0. So then part 2, we're seeing if this is continuous at x equals 4. So we'll check for g of 4, and we have 4 squared minus 16 over 4 minus 4, 0 over 0, which is undefined. So since I can't find this part, one of our rules was that it had to exist. This does not exist. G is not continuous at x equals 4. So we could still have found a limit as x approached 4. We would just have done a little bit of factoring. In fact, for those of you that did do that a little bit, we'll take a look at that route as well. Limit as x approaches 4 of x plus 4 by x minus 4. So the factored version over x minus 4. As long as x is not 4, x minus 4 over x minus 4 is 1. So that's the limit as x approaches 4 of x plus 4. So our limit is 8. But our limit exists. The actual function value does not, so they cannot agree. So g is not continuous. And I've run out of space for that. I'll just picture that written at the bottom where it belongs. G is not continuous at x equals 4. Put that up here, even though it belongs sort of down here. I just wrote too large. All right, so some other continuity ideas for various types of functions. If we have f of x equals c, c here is just some real number constant. Hopefully you recognize that as being just a line. Horizontal line is continuous for all x, so f is continuous. That upside down capital A means for all x. Similarly, if we have f of x is x to the nth power and is in the set of natural numbers, pardon me, my attempt to pause didn't work fast enough. So a power function, so here x is a natural number, so 1, 2, 3, 4, we're not allowing a negative first, negative second. We're not allowing a 1/2 power, things like that. Natural numbers only. F is continuous for all x for that as well. If we have g of x is the nth root of f of x, and n here is odd. Usual rules for an index, n is at least 2. If n is an odd, then this is continuous wherever f is continuous. So if f has some type of discontinuity in it, it does still transfer over to g. But if f of x is continuous everywhere, then g of x is continuous everywhere. If it's a cube root, fifth root, seventh root, etc. If, on the other hand, we have g of x is similar setup, nth root of f of x, this time n is even. Think of square roots. We want to avoid taking the square root, fourth root, sixth root, any even root of a negative. So here g is continuous where two things must both happen. F is continuous and f is at least 0. So square root of 0 is just fine. Fourth root of 0, also 0. We're allowed to hit 0. We're not allowed to go to the left of 0 inside of an even root and still stay within the reals. That'll kick us out into the complex. Okay, so some more examples. Those are just some sort of basic rules. We'll look at some piecewise functions. So f of x is going to be the square root of the quantity x plus 9. So that plus 9 is under the radical, not outside of the radical. And make sure when you're taking down your notes that you can tell this from this. So make sure where you know where your radical ends. All right, so f of x, square root of the quantity x plus 9, if x is strictly less than 7, and it behaves as 3x minus 17 if x is at least 7. and we want to know if we have continuity there. So first of all, f of 7. Here x is equal to 7, so we would follow the second category, so 3 by 7 minus 17, so 21 minus 17 is 4. So f of 7 is 4. Then we look at our limits. Since this is a piecewise one, it makes sense to do left and right side limits since we have different behaviors on the left and right side of this point. So we'll look at the limit as x approaches 7 from the left-hand side of function f of x. So that would be the limit as x approaches 7 from the left of, now left of 7, that would be this first category, smaller than 7. So we follow the root x plus 9. So here, if we get very, very close to 7, 7 and 9, 16, square root of 16 is indeed 4. So the left limit is 4. We'll check to see if the right limit agrees with that. So approaching 7 from the right, so hence the superscript plus. So that is the limit as x approaches 7 from the right side. We're following this guy, so of 3x minus 17. So 21 minus 17, that is another 4. Left and right limits agree, therefore the limit as x approaches 7 of function f of x is 4. Since they do agree, if we came up with different values, then we could say that limit doesn't exist, and we would say we have a discontinuity there. So now we can do our last step. So both of these exist. They are, in fact, also equal to each other. So limit as x approaches 7 of f of x is the same as f of 7. They both happen to be 4. Therefore, f is continuous at x equals 7. So the ordered pair exists, the limit exists, the limit and the ordered pair match. That's what it takes to be continuous. You clear all 3 bars. Any one of them falls apart, you can stop there because you do have a discontinuity. All right, so for this next one, I'm going to ask you sort of a different question, but still in the same vein. So g of x is going to be the square root of the quantity x plus 13. I want to know, where is g continuous? So go ahead and pause that and see if you can come up with an interval. Okay, welcome back. So hopefully you recognize this one as being an even root. X plus 13, x is just in the format of x to the n. Our n here happens to be 1. So that's continuous everywhere. 13 is continuous everywhere. So the inside function is continuous everywhere. We're under an even root, so g is going to be continuous everywhere where this exists and is at least 0. So we just let x plus 13 be at least 0. Just use a little let line, let x plus 13 be at least 0, so x is at least negative 13. So then this would be from negative 13 inclusive to positive infinity. If you prefer the set builder notation instead, set of all x such that x is in set of real numbers and x is greater than or equal to negative 13. Most students of mine stick with the interval notation, but either one will work. And let me have you all try one more. So h of x is going to be a piecewise function, x squared minus 4 if x is less than 2, and it'll behave as negative 3x plus 5 if x is at least 2. And see if you can prove or disprove continuity at x equals 2. Okay, so give that one a spin. All right, welcome back. So first we'll find h of 2. If x is equal to 2, we're following the second one, so that is negative 3 by 2 plus 5, so negative 6 plus 5 is negative 1. So h of 2, not negative 2, h of 2 is negative 1, so this exists. Since it does exist, we'll move on and check limits. Piecewise, we do left and right limits. So we'll do the limit as h approaches 2 from the left. From the left, that's this x squared minus 4. So 4 minus 4 is 0. Limit as h approaches 2 from the right. We listen to this guy, so the 3x plus 5, which is 6 and 5, negative 3x plus 5, negative 6 plus 5, a negative 1. Right and left limits do not agree. Therefore, since those are not equal to one another, the limit as x approaches 2 of h of x does not exist. Therefore, h is not continuous at x equals 2. So we don't even have to move on to the third stage of the test, seeing if the limit is equal to the value at the point, because the limit itself did not exist. So that proved it was discontinuous at that value. Okay, so next we'll look at the theorem that relies on continuity. And you may have sort of applied some of it in your college algebra class without actually proving why it works. So f is continuous on open interval AB, and f of x is not equal to 0 for all x on open interval AB. Then one of two things has to be true. Either f of x is greater than 0 for all x on open interval AB, or f of x is less than 0 for all x on open interval AB. So the idea here is, think of the x-axis as sort of a fence between the positive outputs and negative outputs. So we've said two things about function f. It's continuous, so I'm not allowed to pick up my pen when I'm drawing it. It's also not worth 0, so I can get close to this line, but I'm not allowed to touch that line along interval AB. If one of these is positive, all of them are positive then. Similarly, if I had started down here and followed those same rules. So here's point A, here's point B. So I'm continuous, so I can't pick up the pen. If I were allowed to pick up the pen, I could put a little hole in it and drill through to the other side. If I were allowed to hit it, I could just hit it and cross it. I can't do either of those things. If I can't do either of those two things, I'm continuous on this whole interval. If one point is negative, all of these points are negative. If one point is positive, all of them are positive. So our application that you may have seen in college algebra, again without the continuity proof and the formal definition of continuity back then, we would solve nonlinear inequalities with this. So for example, x plus 7 over x squared plus 3x plus 2 less than or equal to 0. We would just start with a let line, let it temporarily equal 0. I'll go ahead and factor the denominator to make things a little easier. So let that temporarily equal 0. If we multiply both sides by the denominator, 0 times anything would still be 0, and the left-hand side we would have just an x plus 7 left over, so x equals negative 7. So there's one place where this left-hand side that we can temporarily think of as a function is where 0. We also want to talk about where we have discontinuities. We have discontinuities at x equals negative 2 and x equals negative 1. So we have a 0 and a pair of discontinuities. I will write the correct pair of discontinuities this time. So those are what we refer to as being partition numbers. They cut up the real number line. So here's a negative 7, a negative 2, and a negative 1. I'm not super worried about scale. And then we just use the fact that ever or else is following the two rules that we set up earlier, that ever or else is continuous and not worth 0. So I just need to find one point to the left of negative 7. Any guinea pig you want. I'll use a negative 10. You might have picked a negative 8. Your neighbor might have picked a negative 532. Just one guinea pig from each section. So we test it out. For simplicity's sake, I'm going to use the factored version of the denominator with our inequality. So negative 10 plus 7 is a negative. Negative 10 plus 2 is a negative. Negative 10 plus 1 is a negative. And I want to know, is that less than or equal to 0? Odd number of negatives. Result is negative. So negative less than or equal to 0 is true. So it worked for the negative 10. It works for all of the points there. No matter what number you plugged in, you got a true statement when you plugged it into the original. We'll talk endpoints in a second. Between negative 7 and negative 2, I'll use, I don't know, negative 5. Again, if we're comparing to 0 and we use the factored versions, we can just use a sign number argument. So negative 5 plus 7 is a positive. Negative 5 plus 2 is a negative. Negative 5 plus 1 is a negative. And we want to know, is that less than or equal to 0? Positive less than or equal to 0 is false. So if this one doesn't work, none of them work. Then something between negative 2 and negative 1, so negative 1.5 will be just fine. Again, I can use a sign number argument. Negative 1.5 plus 7 is positive. Negative 1.5 plus 2 is positive. Negative 1.5 plus 1 is negative. And I want to know, is that less than or equal to 0? So negative less than or equal to 0 is true. I want all of this stuff. So then I'll test this last chunk. 0 is fine. Just anything on there. Again, you might have picked out 25. Your neighbor might have picked out pi. Someone else might have picked out 999 trillion. As long as it's from that section. If one of them works, all of them work. One of them fails, all of them fail. All right, 0 plus 7, positive. 0 plus 2, positive. 0 plus 1, positive. And I want to know, is that less than or equal to 0? So I've got my little question mark there. Positive less than or equal to 0 is false, so I don't want that. And then just make sure you fight your instinct to put brackets on all three of these guys with the or equal to. Remember, we're still never allowed to divide by 0. So no matter what happened with these guys, -2 and -1, we're always going to have parentheses. So what we get to keep, negative infinity, which we can only approach, so that gets a parenthesis, up to and including the -7. And then we union that with -2 exclusive to -1 also exclusive. So in section, yeah, I wasn't going to be able to squeeze it on there. In section 2.3, I would recommend 1 to 55, every other odd, 61 to 73 on the odds, and 83 to 86 all. And again, I'll load up the my math lab sort of default 2.3 assignment. It might be a little bit different than mine. But some of you do like working with my math lab stuff as well. Okay, if you have any questions, please get in touch. Otherwise, I will see you next time. Stay safe out there.